Hello everyone, welcome to all in this lecture. So in this lecture, I'm going to discuss design of shallow foundation. Or in that design of shallow foundation, I will discuss rectangular combined footing. So what is combined footing? Combined footing, which is support the two columns loads, we design for support the two columns load. So there are two cases. There we have to go for the design of combined footing. So suppose in the first case, I'm saying like suppose this is the property line and one column is here, okay, and second column is here. So we need to give some projection for their column. So what is the problem coming in this column? Suppose this is the exterior column and this is interior column. So we cannot give the projection on this direction. So what we do, we just provide a combined footing, and that combined footing will join this exterior column to the interior column. So we go for the combined footing. So in this case, we need to design a combined footing. In other cases also, suppose this is the case one. In other cases, what will happen? Case two, we can say when you will see there is a footing, isolated footing, and here is also isolated footing. So you will see there is a overlapping. Suppose this you are getting some overlapping, okay. So in this case, when you are getting the overlapping of footing of the two isolated footing, so we need to design combined footing. So better we design combined. And there is some, so there are two types of combined footing. One is the rectangular footing, another one is the trapezoidal combined footing. Rectangular combined footing means rectangular, the plan we will see that shape of the rectangular. In trapezoidal, if we will see the plan, there is a trapezoidal in shape. So suppose the column loads that is coming on the exterior, that is a Q1, on this interior, that load is coming Q2. So when Q1 is less than Q2, Q1 is less than Q2. So in this case, we can go for design a rectangular footing, rectangular combined footing. So by doing this, we can get the uniform pressure distribution at the base. Suppose Q0 is the actual, so this will be the uniform pressure distribution. And one more important thing, whenever we want to get the uniform pressure distribution, what we have to do, suppose the resultant is coming, suppose this is Q and that is resultant of the two column loads. So the center of gravity should be lying on this line. Center of gravity should be lying on this line, center of gravity of footing. So by doing this, we can get the uniform pressure distribution. So whenever we will calculate the length and width of the rectangular combined footing, we have to do this. Whatever the resultant coming on this load, resultant of load coming on this line, so center of gravity of footing, it should be lie on this line. So by doing this, we'll get the uniform pressure distribution at the base of the footing, right? Okay. So other case I'm going to discuss here. Suppose in this case, rectangular combined footing is suitable. And the other case, suppose Q1 is greater than Q2. So by providing the rectangular combined footing, we cannot make it uniform pressure distribution at the base. So in this case, we have to go for the trapezoidal combined footing. B1, suppose this is the B2, this is the length. So we have to go for, suppose this column load is greater than Q1. So we need more area at the base of the footing in this case, and we need less area in this the footing. So by providing the rectangular combined footing, we cannot do that. We cannot make the center of gravity cannot be lie on the resultant of the loads. and pressure distribution will be not uniform. So for that case, we should go for the trapezoidal combined, right? So in this lecture, I'm going to discuss only rectangular combined footing. In the next lecture, I will discuss trapezoidal combined footing, right? Okay, so let's start. Let's discuss this rectangular combined footing. So in this figure, you can see two view. There is a plan view, another front view, or cross-sectional view, you can say. You can see this. So here Q1 is the load, column load on the exterior column. Q2 is the load on coming interior column. The resultant, we can say this Q is resultant. You can write R also, resultant Q minus plus Q2. So this resultant is acting at a X bar distance from a center of exterior column. Okay. This here Q naught is the actual pressure. How we can calculate actual pressure? By dividing total load divided by area that is provided, not required. We always provide some more area provided. So by doing this, we can calculate actual pressure. Here you can see X2, that is the center to center distance between both column. Okay, and there is a plan view also. So you can see this is a rectangular combined footing. Their width is capital B, length is capital A, and a cross section of this exterior column, that is B1 into B1. Here the cross section of the exterior column, that is B1, B2 into B2. So you can see by figure, there's a cross section area for this interior column is more as compared to the cross section area of exterior column. So we can say in this case, by seeing this figure, we can see Q1 is greater than Q2 is greater than Q1. Means loads coming on the interior column is more than loads coming on the exterior column. So when condition is this, we can go for the rectangular combined footing. Okay, so there is some procedure that we have to follow when we are going to design rectangular combined footing. First, we have to calculate what will be the total loads that coming on the footing and what will be the resultant loads that coming on the footing. So here you can see two loads or two column loads are coming on footing, that is Q1 and Q2. So we can calculate total or resultant loads. Next, we can calculate A, that is required area. Here the A is the required area. So we can calculate Q by QNA, where the QNA is the QNA is allowable soil pressure. Here the QNA is allowable soil pressure. So next we can calculate what will be the distance of resultant loads from the center of exterior column, that is shown in the figure, that is X bar, right? So we can get this. How we can get? I'm discussing here. So suppose the resultant, whatever the moment I'm calculating from this point, suppose this point is P. So moment about this point total resultant. So we can write Q into X bar equal to Q1 into, you can see Q1 distance and lying at this point. So it will be, this will be 0. Q2 into, so this distance from here to here. So that is given X2. So here we can write X2. I'll get your point. So we can calculate from this equation X bar is equal to Q2. This will be the 0. Q2 into X2 divided by Q. So same thing I've written here. Okay. So now we can we can calculate total length. So this is very important to understand what is the meaning of this. It means you have calculated the X bar from the lesser load. So always lesser load. So what is the meaning of this X bar? And suppose this distance, this line from this center. This is the higher load. So what is the distance? Let's write x3. Suppose x3. So you will say, you can calculate from here also. You will see that x bar is greater than x3. We'll see this condition because Q1 here the lesser load. So center-wide, the resultant loads from the center of this exterior column will be more. I'll get my point. Will be more. So here x bar is greater than x3. So what we will do, we will select half length by keeping this side, What I mean to say, suppose you get this is a resultant and the distance of this would be x bar and this is the load Q1. Are you getting a point? Okay. So what we do, first we decide what will be the length L by 2, half length of rectangular combined footing. So how we will decide? See, x1 bar is this, and this length that from we can write from the hair, see the cross section. So this is this the B1 plus 2, right? So we can calculate this length from this length. So that would be the x bar plus B1 by 2, right? And we take as a this is the half length of rectangular combined footing. This is a half length of rectangular combined footing. Always remember, we cannot do this when you are working or you are calculating from the distance from the that larger column loads side. Always remember, we have to calculate from the lesser load side. So it will get the x bar is more as compared to the x3, right? So what will be the length? 2 into x bar plus v1 by 2. And by doing this operation, it means, suppose this is the column load and this is the length, like L by 2. And then you are taking the L, right? So what will be the center wide of this footing? Tell me, what will be the center wide of this footing? So center wide of the footing will be here, and that is coincide with the resultant load. So that's why we take from this point, we take length, half of length rectangular, then we multiply by 2, take the total length. So the center wide will be here, right? So by doing this operation, it means you already have considered that resultant line, that center of gravity of the footing lying on the resultant of the loads, right? Okay. So are you getting my point? Now, we have the length, then we can calculate for the width of the footing. So that we can calculate B equal to A by L. Here area, here area is provided area, right? Here area was C. This area is the required area. Okay, and this area what we have provided, cannot use required. We have here is some here is provided area, right? Okay. So now we can calculate actual pressure Q naught, actual pressure at the base of the footing, and that will become Q divided by A naught. A naught, which is provided area or actual area. So this will be also we can write B is equal to A naught divided by L, right? Okay. So now we have the actual pressure at the base of the footing. So now we can calculate then what will be the UDL, uniformly distribution load, right? So I'm explaining here. Suppose this is the pressure that we got. This is the pressure. This is the pressure. And now we want to calculate what will be the Q1 into Q1. What will the UDL? UDL, uniformly distributed load. So that we can calculate or we can draw the shear force diagram at various points where we can draw shear force diagram, or we can draw a bending moment diagram so that we can calculate maximum or minimum bending moment and bending moment at every cross section wherever in need. So that we have to calculate what will the UDL. So simply UDL, uniform distribution, we can write Q naught, that is pressure. In what direction we want? We want working in L direction. So we have to multiply what is the depth or what is the length perpendicular to this figure. So that is, if we draw a rectangular, this is the B and this is the total L. So it will be Q naught into B, Q naught into B. So this is the UDL, right? So by calculating this UDL, after calculating the actual pressure, we can calculate the UDL. And once we have calculated the UDL, then we can draw the shear force diagram and bending moment diagram. See, I'm saying the length and width we have already calculated, so our work is done. But we will also draw the shear force diagram, bending moment diagram, so that if we are going to design the reinforcement on concrete design, so we need the bending moment, and for the critical section at various critical section, we need diagonal shear force, what will be the critical section, so that we can decide the depth of. So we will do that procedure, like draw the shear force diagram, bending moment diagram, and further we are not going to design the reinforcement and concrete. Okay, so the step 7 is draw the shear force diagram, bending moment diagram along the length of the footing. And next is the determine the bending moment at the face of the column and the maximum bending moment at the point of zero. Once bending moment is drawn, bending moment diagram is drawn, we can find bending moment at any location, at any points or any critical, at any section, right? Same we can do for the diagonal shear also. So that thickness of footing for the fine bending moment. So there is also there is some procedure by mention. If we are going to design the reinforcement, so that is mentioned in the IS code 456/2000. Then check the diagonal shear and punching shear as in the case of the isolated footing. So for the isolated footing, like this two footing column, we can go for the checking the different shear, like one-way shear and two-way shear. That we can go. So whatever the shear is coming on that, so once we have drawn the shear force diagram, so if whatever the shear force at any location, at any cross section, or any critical section, we can find and determine the longitudinal reinforcement for the maximum bending moment. So that is not our work. At a geotechnical point of view, we are going to design, or we are going to draw only the shear force diagram on bending moment. So whenever we will see any problems, so we have to decide length, width, and then we can go for the shear force diagram and bending moment diagram for the combined footings. Okay, so let's discuss some of the numerical problems so that we can understand more and more. So the first question we have a design rectangular combined footing. Rectangular combined footing. For the two columns shown in the figure, take the allowable soil pressure 100 kN per meter square. So this is the QNA. Here the column loads 900 kilonewton. Here the Q1 is the 600 kilonewton. So you can see this projection, it means we cannot go here. And in this case, you can see there is a Q2 is greater than Q1. So we can go for the rectangular combined footing, which is mentioned in the question. And what are the other data is given? So you can see there is a given a cross section of lesser column load, that is B1 into B1. Here the cross section is given for the higher column load, B2 into B2. Okay, and distance between the two columns are given, that is 5 meter. That is 5 meter. So here the center, this distance between the exterior face of this column to the center, it would be total is B1 0.3, so it would be 0.15, that is mentioned here. Okay, so distance between centroid of two column loads, that is given 5. You can see here 5 meter. Okay, so here this case it will be not mentioned here. Okay, so this is given for this for now. This is not here. Okay, I will calculate later. Okay, so let's go to calculate. So what we will do, we will just follow the procedure what we have mentioned in the previous slide, right? We will always follow the procedure. If you will work according to the procedure, you will not find any difficulty. So on the procedure, what we have, then what we will calculate according to that, what we will calculate for next. So all things are mentioned here. So for the first procedure, we will calculate the total resultant load, that is Q is equal to Q1 plus Q2. So we have the two loads, 600 kilonewton, another load is 900. So we can calculate. So that will become in the 1500 kilonewton. So now we can calculate what area is required. So Q divided by QNA, we can calculate, and that we get 15 meter square. 15 meter square. So next procedure can follow. So in the next procedure, we are calculating the X bar. Like what is the X bar? X bar is the center of distance of centroid resultant of loads from the center of the exterior column. So here is not mentioned. I am drawing here. So X bar is here. The previous slide also I have discussed this one. This is the X bar, and this is the Q. That is Q1 plus Q coming in. So that we get 3 meters. So this we get 3 meters. So what will next? So next we can do total length. So total length 2 into X bar plus B1 by 2. So here the B1 is 0.3 and X bar, that is we have calculated in the previous procedure in the 3 meter. So by doing this we can get the total length 6.3 meter. Now we can calculate the width of footing. So here I'm whatever the area required, we have provided that same area. You can say no, we have calculated the whatever the width required, that is B, A by L. So we have divided 15 by 6.3, we get 2.38. So now we are assuming that we are providing width 2.4. So when you are changing the width and length, so whatever the actual area will be different from the required area. So now we can calculate actual pressure by dividing the total loads to the actual area we can get. So you can see here actual area is 6.3 into 2.4, not 2.38, 2.4. Suppose you have provided 2.5, so you will write 2.5, not 2.38, right? So by multiplying these two quantity, we'll get the actual area or provided area, we can say. So actual pressure we have 99.2 kilonewton per meter square. What is the next? Next, we will go to calculate UDL, uniformly distributed load. So Q naught into B. So here also we can write B 2.4. So 99.2 into 2.4 will get 238.1 kilonewton per meter. Right? So we can say this is the UDL. So now once UDL we have, so that's this thing I have written already here. So now we can draw. So we can say by doing this operation, uniformly pressure distribution will act at the base of the footing, and that we get this. So this is the showing uniformly distributed load. That is 238.1 kilonewton per meter. Are you getting my point? Okay. So what is the next? So next we can draw shear force diagram and bending moment diagram, right? So see, whatever the columns and footing were there, just make a line diagram of that. So I'm drawing a line diagram. This is the length. So what we are going to do here, Q1, and here Q2. Distance between both column loads was 5 meter. Am I right? And total length. So I'm not writing total length. So what will this projection will come? Tell me, what of this projection will come, so that we can calculate. We can write in the previous section. We can see this is a 0.15 5 meter, and then we can calculate. So this we can calculate. So total length we have, that is calculated, that is 6.3. So here this is 0.15. From here to here, that is 5 meter. So we can calculate this one. So what will become? Okay. So, and this is the pressure is acting here. This is the pressure is here, and that pressure is what we get, 238.1. So this is the uniformly pressure. We can set the soil reaction also. That is 238.1 kilonewton per meter. So now we can draw the Mohr circle. Sorry, not Mohr circle. We are going to draw the shear force diagram, bending moment diagram. Okay, not Mohr circle. Okay. So all distance we have here, the distance is 0.15, then 5 meter. Here it will come 1.15 meter. So by adding this, we can get 6.3. Okay. So what is the procedure to draw shear force diagram? Okay. So first take the sine convention. So we are taking the sine convention. This left side direction, what is positive, right side downward is positive. So let's draw the Mohr circle. I am saying always Mohr circle. Shear force diagram, right? Okay. Sorry. So let's start from the here to the left. So you will see here in this, here there is a upward direction. There is a load in the upward direction. Okay, so this will be negative. So we can calculate and give some name, like this is the point A, this is the point V, this is the C, and this is the C. Okay, and the end point is D, A, B, C, D. Okay, so we can say the shear force at a point A, there is no point load is acting, so that will be a 0, right? Now shear force at a B point. So you will see there is a upward UDL is acting, that is 238.8, 238.1. So the distance we can calculate, and sine convention we have taken, downward is positive and here is acting upward, so that's really negative. So negative W into X. I'm writing in a general expression here, the W is the UDL load and X is the distance. So you will see 238.1 into 1.1. What you will get? Just calculate. That will be the kilonewton. Okay. Now we can calculate shear force at a section. Suppose XX, and that XX I'm assuming somewhere here, right? Okay. And I'm assuming that distance X works when it's from the X distance from this point, right? So we can write UDL load is there, so that will be negative W into what is the total distance from here to here, right? It is acting on this length, so that will come X plus 1.15. Okay, now you can see that load is coming downward, Q2, and so that will be in the positive, and the value of Q2 is 900, right? So this is the general expression we get. W, that is minus 238.1 to X plus 1.1 into 900. So now we can calculate shear force at C. Shear force at C, okay, just below, just before the C, we can say. So that will come. And when we are working here, so what will be the value of X? So X will be 5 meter. So by keeping X equal to 5 meter, we can get shear force at C. So we can calculate minus 238.1 into 5 plus 1.15 plus 900. We'll get some value, just calculate. And you will see there is a Q1 load is acting just downward. So you can say here also that you will see, I will discuss here. So the here, and at a shear force at a D, if you will calculate from the right side, again there is no force. If you are calculating from the left side, from the left side, so it will become 0 directly. Okay, so I already have drawn the figure that is mentioned. So we'll get this shear force diagram. So now I can write the value, and you can check the value also whether you're getting the same value or not. So shear force at the B will come here minus 273.8. Okay, or on the shear force at C will get the value minus 56.4 kilonewton. Here this value is minus 273.8. If you will calculate at the point C on the from the left side, you will see there is a change in the 900 kilonewton, because 900 kilonewton is concentrated load acting at that point B. So you will say see the sudden change, because this will be the negative. So here adding the 900 kilometer. So by addition of 900 kilo, you will get this. Here also there is a negative of 560 minus 564 minus 564 kilonewton, and there is a total load is coming 600 kilonewton. So we'll get that is in positive. We are coming from the right side. So we'll change. We'll get the change. So that put plus 36, automatically it will come. So whenever you will see the UDL load are there, so on acting on the beam on whatever, so you will see there is a linear variation of shear force diagram. There is a linear variation. There is a linear variation of shear force diagram. Okay, so I think we are very clear about the shear force diagram in this case. Okay, so let's go to draw the okay. So we can now go to draw bending moment diagram. So let me hit something. So same UDL will act here to 238.1. Okay, and the length and load are given. So that is Q1 and Q2 load, that is 600 kilonewton and 900 kilonewton. So we can go to draw. So there is also a sine convention we can take. So I already have can show figure, and I will tell you what value we can get. So this is the bending moment diagram. I will explain how we are getting this. So we have taken the assumption of sine convention. This, if you are coming from the right side, if you are coming from the right side, so we'll see there is a clockwise direction will be the positive. But if you are working from the left side, there is anti-clockwise direction positive. So let's calculate. So bending moment at a point A, what will be at a point A? So we'll say you are here, right? You are here, right? So this will be the 0 because there is no force. Now we can calculate in between bending moment. Suppose x and x-axis is here somewhere, right? So we can write general expression. So that will be the C. Here the this UDL load is acting in an anti-clockwise direction. So that will be in the negative according to our sine convention. So we can write W into X, that is distance of X from this, right? Okay, and this is the load and central gravity of the load from the X section. So that will be the x by 2. So we can write minus x square by 2. And that section is valid from the B to A. So by putting the x is equal to 0, we will get the bending moment 0. Okay. By calculating, by putting the x is equal to, by putting x is equal to 1.5, we will get the bending moment at B. So minus W, that is 238.1 into x, that is 1.15 square divided by 2. So we will get minus 157.5 kilonewton per meter. Here two important things. So suppose this you are drawing, or you have started to draw the more bending moment diagram. Okay, so here at the point, this is point A, this is point B. So here is 0 and here is minus 1. So you will draw like this, or you will draw like this. You will draw like this. How you will draw? What will be the curvature? In what direction? There is a concave or convex. So there is a mathematical expression for that. There is mathematical rules we have to apply. So what we have to do for that? So this is the general expression, bending moment. This is a mathematical section, but I am going to discuss because we need. If you don't know about that, if you don't have any idea about that, so you can get some idea about from this. So bending moment, that general expression minus x square divided by 2. So we can write, differentiate the bending moment from the x. You will get minus w x, right? Again, you can go for the differentiation. You will get minus w. So what is the meaning of this? When you are increasing the, you can see the double differentiation of bending moment with respect to x square. Here it will be x square t x square. So this is negative. This is negative, right? It means the slope is continuously decreasing. Slope is continuously decreasing. When the slope is decreasing, we'll say there is a concave downward. We'll say concave downward. This is a concave downward and this is a concave upward. So by doing this operation, we can say, suppose this अगर ये हमें positive आता है, it means we will draw like this. Draw like this. But here in this case we go minus w. It means double differentiation of bending moment with respect to x is coming. Negative, it means here it will case of concave downward. So this will be the correct. So that is written in here like this. Like this is the case of concave downward. So whenever you got some confusion, so always do the operation. First we calculate bending moment with respect to x. Then you go for bending moment. Double differentiation with respect to x. So we'll get the what will value. According to that, you can guess the idea whether it will be concave down or concave up. Right. So let's go to calculate the next. So now what we can do, we have to calculate the bending moment at a point C. At a point C. So first, right, we can write the general question. So now we have to take the x-axis at in between the B and C. So it will run from the B to C. So now we have, suppose this case x1, the given name. So write the general expression bending moment at x1. At x1 axis, what will be there? So first write down the UDL. So what will be the UDL? So what will be the UDL? So UDL is 238.1. So, and that will be in the negative. So minus 238.1 into what is the length? So suppose this x is here, so this length is x. Okay, so we can write x plus 1.15 1.15 into, and this is the total force. So it will act at a center point. Center point will be x plus 1.15 divided by 2, right? And now you can see here Q2 load is acting downward, so it will give the clockwise moment. So we can write 900 into x. So this expression will be valid when we are calculating from B to C. So now we can calculate bending moment at C by putting the x is equal to 5. By putting the x is equal to 5. So you can get minus 238.1 into 5 plus 1.15 into 5 plus 1.15 divided by 2 into 900 into 5. So we'll get minus 2.7 kilonewton. You can check the variation also by differentiation this equation by from the x. So we'll get at what point, at what location where the maximum bending moment will be maximum. So how we can get, we will do this operation, bending moment divided by dx. By equating this, you will get at what value of x, this will be the maximum, and you will get the maximum value at a from this to this 2.63. By calculating this shear force diagram also, you can get where the shear force will be 0 by putting this shear force is 0. So we'll get the value. So this will get the 2.63. So this you already studied in the structured subjects. So this is a very basic, and I would say to draw a shear force diagram and bending moment diagram for any structure or any cases, you will see. So that topic is very, very important. And when you are going to analyze, do the analysis, when you are going to do the analysis of any structure, so these two are very important, because by drawing this figure, we got the idea at what location, at what critical section, at what position, what will be the shear force and what will be the maximum bending moment, what will be the negative maximum bending moment. So in this both the cases, you can get the whole idea. And whenever you are you have some, if you have some idea about the design, so you will see whenever the critical section, so we need at that critical section we need shear force, we need the bending moment value. So according to that, we design other section like depth of the footing and concrete, and then reinforcement, what will be the depth of foundation, all those things. So this two diagram is very, very important, I would say, and you have to know each and everything about this. So I got like in this question, I have to draw the shear force diagram, bending moment diagram. But if you are studying other subject, you have to draw shear force diagram, bending moment, different structure like frame structure, like truss and all those things. So you have to be very clear about this concept. So I'm not going to discuss in details. By drawing shear force and bending moment diagram also, we can go for in details, but my subject is not related to that, so I'm just explain. But you can study in this all the diagram and how we can draw this diagram in a different structure. So we have to go in details to study in depth. Okay. So these are some references that I have for this structure I've taken. So thank you. In the next lecture, I will discuss the trapezoidal combined footing. Okay, and in this next lecture, I'll also discuss one numerical problem, so you can get the idea. And you will see there is some procedure are very similar to the whatever we have already seen in the rectangular combined footing. So that is same will use the trapezoidal combined footing. Okay, so thank you. So before I'm writing any calculation on any value, so what we will do, just take the pen and paper and calculate whether you are getting same value or not. Don't see the ideal and just watch this lecture, what sir have written and all this thing and just writing in your copy. Just use your brain, use your calculator, okay, and try to solve by yourself. Then you can see whether I'm getting the same answer or not. If I'm not getting the same answer, got all I can do the error also. So when you are not getting the same answer, just comment this comment section. You can send a message in the WhatsApp. Okay, so always keep some calculator, keep calculator, and by watching this lecture, try to be solved first by yourself. Okay, okay. Once again, thank you.